Hello all, welcome to the webinar series of IEEE Joint MTT APEMC Chapter Islamabad. I'm Dr. Roshan Shoaib, the chair of this chapter, and I'm also working as assistant professor at Research Institute for Microwave and Millimeter Wave Studies, also known as RIMMS, at NUST, National University of Science and Technology, H12 campus, Islamabad. So Islamabad is the capital of Pakistan. We are located in Islamabad, is one of the well-managed and among the beautiful capitals in the world as well. It consists of both business hub and natural beauty as well. And this is a place where we will conduct next year the Pakistan's first dedicated international conference on microwave antennas and circuits, ICMAC 2021. We will announce the dates for the call of paper in coming months. I hope most of you will join us and come to Pakistan to present your findings and talks. So National University of Science and Technology has several campuses, and this is the bird's eye view of the Islamabad campus we have, and the RIMS is located here. This RIMS, also known as the Research Institute for Microwave and Millimeter Wave Studies, is a specialized postgraduate institute that offers MS and PhD degrees in electrical engineering with a particular focus on RF and microwave. Apart from our theoretical concept, we also have the state-of-the-art lab facilities, including anechoic chamber that works up to 40 gigahertz for antenna characterization. We have the EMC EMI lab that is used for the pre-compliance testing of the system. We also have micro research and antenna lab, and also have an in-house PCB fabrication facilities, so the student can actually develop the circuits and antennas within under the one platform, and also characterize it under the same institute. This will give an opportunity for our students to get a hands-on experience apart from their theoretical learning. So we are very pleased to welcome Professor Markus Gardill from University of Würzburg, Germany, today as our speaker. The webinar title is Automotive Radar, a Signal Processing Perspective on Current Technology and Future Systems. A few lines about Professor Markus Gardill. Professor Markus Gardill is a professor for satellite communication systems at the chair of computer science, robotics, telematics at the University of Würzburg. He received the diploma engineering and doctor engineering degree in the systems of information and multimedia technology, electrical engineering from Friedrich Alexander University, Erlangen-Nuremberg, Germany in 2010 and 2015 respectively, where he was a research assistant, teaching fellow, and later head of the team for radio communication technology. Between 2015 and 2020, he was an R&D engineer and the research cluster owner for optical imaging metrology system at Robert Bosch. Later, he joined Innocent as a head of the group Radar, Signal Processing and Tracking, developing together with his team new generation of automotive radar sensors for advanced driver assistance system and autonomous driving. His main research interests include radar and communication systems, antenna array design, and signal processing algorithms. His particular interest in space-time processing such as beamforming and directional variable estimation together with cognitive and adaptive system. He has a special focus on combining the domains of signal processing and microwave electromagnetism to develop new approaches on antenna, array implementation, and array signal processing. His further research activities include distributed, coherent, and non-coherent network for advanced detection and perception, machine learning techniques for spatial signal processing, highly flexible software-defined radios radar system, and communication system for new space. Professor Markus Gardill is a member of IEEE Microwave Theory and Technique Society. He served as a co-chair of IEEE MTTS Technical Committee Digital Signal Processing MTT9, regularly as a reviewer and TPRC member for several conferences and journal paper, and currently serves as associate editor on Transactions on Microwave Theory and Technique. He is a distinguished microwave lecturer for the DML term 2018-2020 with a presentation on signal processing and system aspects of automotive radar system. We are very pleased to have him on board, and I request now Professor Markus to please proceed ahead and start the webinar. Over to you, Professor Markus. Thank you.
Okay, so thank you for this kind introduction, and I will start sharing my screen now, right? Which is this one here. Okay, so here we are, ready to set. I think you should all see my slides now. And yeah, now it's my pleasure to welcome you to my presentation on automotive radar, with a special focus on not, let's say system or subsystem implementation, but with, let's say, the broad perspective on, the automotive radar market application and the particular focus with the signal processing perspective on current technology and future systems. Now, if you are interested in the slides of this presentation, then you can find the full slide deck here on my private website. Basically, it's a pretty large set of slides, about 130 slides. So of course, we won't have a look on all of those slides today in the presentation, but you find the full slide deck online. And today we'll give you, let's say, or present you a subset of those slides. Well, of course, I'm a distinguished microwave lecturer, and typically it is also the IEEE budget, which is available for us DMLs traveling around the world and bringing basically us as speakers to you, to your societies. Unfortunately, due to COVID, that's not possible at the moment, so we do have this virtual presentation. But of course, still, it is an IEEE sponsored talk. So here's just some advertising slides. Of course, if you are not yet a member of the MTT Society, then please consider all those benefits you have when becoming a member, like access to the Microwave magazine, to the newsletters, so you stay technical current. And of course, we do have an excellent society for professional networking. So if you are not yet MTTS member, then maybe have a look at the MTTS website and consider becoming a member of IEEE MTT Society. Now, but let's basically start with the presentation. And first of all, I would basically tell you, well, why I am Mr. Markus Gardill talking about automotive radar systems. And the reason for that is that basically before I joined university, so before I went back to academia beginning of this year, beginning of 2020, well, I was working in the automotive industry. Since I was head of the team for signal processing and tracking at a German company, which is called Innocent, which is for innovative sensor technology. And Innocent was founded about 20 years ago and has its origins in industrial radar systems, like building low-cost mass production radar systems, for instance, for automatic sliding door openers, or also perimeter surveillance or law enforcement, like traffic monitoring, speed monitoring. So it's a medium-sized company which has around 170 employees, but manufactures around 3 to 4 million radar sensors here in the northern part of Bavaria in Germany. And since, I would say, 10 years ago, Innocent also entered the automotive market. But of course, with just having 170 employees, your company typically is much too small to act as a direct supplier to the automotive manufacturers. And therefore, Innocent basically is part of Hella, and Hella is a big German tier 1 supplier for automotive components, and also had a worldwide relatively large market share in automotive radar systems, and they are located here in Lippstadt and also do have an office in Berlin. And together, Hella and Innocent, where Innocent is typically the pre-development center for Hella, basically they do have a worldwide footprint for industrial and with Hella automotive radar systems. So that's why basically I'm talking about automotive radars. And now really let's dive into automotive radar sensor technology. Now, if you look into today's car, then basically you have 4 types of sensors which are used to monitor the environment, the surroundings of your car. Now, we do have the cameras, we do have radar, of course. Then in future cars, of course, there's a lot of activity in bringing Lidar into the cars, and the mass product is the ultrasonic systems. Now, if we kind of try to categorize those sensors, then of course we can see that all of those are made for detecting traffic participants, because I mean that's the goal of all of those different sensors used in the cars. But for instance, if you look at the capability of doing texture interpretation, what you for instance need to detect the lane markings on the road, then you see that basically the camera is the only sensor technology which can do this. Of course, you cannot detect lanes with the radar, you cannot do this with the Lidar, and so not with the ultrasonic systems. And the same is true if we look at different, let's say, features like ambient light independence. Then we see, of course, radar has absolutely not a problem with ambient light changing conditions. Lidar does not have a problem, ultrasonic systems not, but camera has some problems. Camera needs some time. Of course, if you're coming, for instance, from a dark parking garage into the bright sun, the cameras need to adapt. You need some active illumination if you want to use the cameras at the night. So we see camera has some challenges here, and this is also true for different features. And basically what this slide should conclude is that there won't be a single one sensor technology which will win the race if it comes towards autonomous driving. Okay, so basically it's not a question, will radar be better than camera or Lidar, but the basic question is that we will always need at least two of them. Okay, so we will always need a sensor data fusion basically to provide a check mark in each of those required features. The typical team you have today on the streets is the camera and the radar. Camera typically mounted behind your central rear mirror looking at the streets, and then the radar sensors, and both do data fusion to get the necessary reliability in changing weather conditions, for instance. In the future, maybe we will see also Lidar systems. For example, the new Audi A8 and Q8 generations are the first series cars who do have a Lidar system in the front bumper. And I think the ultrasonic sensors will maybe get out of the cars, because basically you can do everything with a modern radar, like parking and extreme near field detection, what you can also do with the ultrasonic sensors. So if we do have the modern cars have at least 4, 5 to 7 radar sensors, then there won't be any need for ultrasonic sensors anymore. Now, automotive radar, well, how does because this is a radar talk, so now we'll neglect all the other sensor technologies and we will focus a bit more on the radar. So how does the radar work in a nutshell? Of course, we do have a radar sensor. We emit a waveform, an electromagnetic waveform, which propagates through space, hits a couple of targets, which we do have. Those targets scatter this incident energy, kind of reflected back to our radar sensors. So we do receive the echoes, and then what the radar sensor does at first is a channel estimate. And this is very similar to what you do in communications, where you basically estimate properties of a time variant channel. Okay, but in radar we do have to do more than just this channel estimate, like a time variant Doppler response or whatever, because what we do have to do in radar is to estimate the physical geometry from this channel estimate. And this, I would say, is the big difference or the big add-on of radar to communications, that we really are interested in this physical geometry. I mean, the relation between channel response and geometry is simple if you are just considering a scenario like this, where you have isolated point scatterers in free space, for instance. But now consider that you do have a reflecting surface here. What you then would see in the channel estimate is basically 6 targets. Okay, but physically you do not have 6 targets, but you do have a reflecting surface and 3 targets, and this exactly has to be resolved in this geometry estimate, and this can be quite complex, for instance, to really detect those reflecting surfaces. And you always do have reflecting surfaces, or maybe in most of the times, because at least in Germany and a lot of European countries, you do have, if you're driving on the highways, you do have the lane borders or road borders, which are made from metal. Okay, and so we do see all the cars to the left and to the right, maybe several times. Now the question is, in which frequency bands do we operate the automotive radars? Well, traditionally automotive radar was operating in the 24 GHz band, where there is still an operational band of about 200 megahertz of bandwidth from 24.05 to 24.25 gigahertz. There also was an ultra wide band which offered a relatively large sweep bandwidth, but this one is going out of service, so it's grayed out here a bit. And of course, all modern developments focus those 77 and 79 gigahertz band. So we do have the 77 gigahertz band from 76 to 77 gigahertz, and the 79 gigahertz band is from 77 to 81 gigahertz. And the presentation today will also have a main focus on those modern frequency bands. Of course, you can never ever have enough frequency, so there is some activity for automotive use in the 60 gigahertz bands, which basically was opened by FCC also for automotive use a couple of years ago. And of course, especially in research works, you see a lot of ideas going above 120 gigahertz applications. Now the question is, why is radar so good for automotive use? And basically I tried to condense this on that slide here. So radar basically is the only sensor technology which gives you, if you do a single measurement, a 4-dimensional image. So typically an automotive radar sensor does one measurement every 50 milliseconds. So every 50 milliseconds you get kind of a picture, okay? And this picture, because this, let's say 50 millisecond cycle is typically one requirement from the automotive customers. So this your necessary update rate. And when you take them one measurement, you get a picture of your scene, and this is a 4-dimensional picture. Why? Because if the radar does one measurement, you get the range of the targets, you get the angles, so azimuth and elevation. And what is unique to radar is, due to the Doppler effect, you also get the radial velocity of all of your targets. And this is unique to radar, a unique feature. Then radar is also very robust towards weather conditions. So in those plots, we see the nominal range versus the effective range of radar, shown here in purple, versus Lidar, so laser, shown here in blue. Basically, those plots are taken from a publication from McCloskey in 2017. And you can see, for instance, in snowfall, dependent on the amount of snowfall, you have a large impairment of the laser technology. So the effective range is much smaller than the nominal range, but we do have, absolutely, I would say absolutely, or almost no impairment for the radar systems. And the same is true for fog, mist, and haze, where you can have, for instance, in fog, a large impairment, which means no really operating nominal or effective range for laser systems. Okay, so radar is very robust in adverse weather conditions. Then radar also is typically the only sensor technology which you can hide invisibly behind a bumper. Of course, you cannot mount a camera behind a bumper. You also cannot mount your Lidar sensor behind your bumper. You also cannot mount the ultrasonic sensors just simply behind your bumper, because you always need, you see those circles in your bumper, some acoustic, let's say, good interface to the air. So you can do this, and except the single front radar, you also typically always do this for rear corner radars, for instance. They are always mounted behind the bumper. But I also asked the question, okay, who was that guy actually who told the automotive manufacturers that you can mount a 77 gigahertz microwave system with a bumper where the bumper might have metallic paint? It is possible. We typically have to do this today, but you easily lose a lot of power. So even if you do everything perfectly, find the right sensor mounting position and sensor alignment with respect to the bumper, you easily lose 6 to 10 dB. Just by this integration behind the bumper, which means if your sensor, let's say your detection range is limited by SNR, and you would take the sensor out from behind the bumper, then you could, for instance, easily increase a detection range behind the bumper from, I would say, 100 meters to 150 meters if you would take it out of the bumper. So the question is if this effort is really worth it, if it's really worth it to have this nice invisible design with the sensors behind the bumper. And then radar also, I would say, is a sensor technology which has a very good trade-off between range and field of view. So typically detection range necessary today is about 160 meters for long range applications. And this detection range means that at 160 meters, the radar is sure that there is an object, which means that the detection of raw targets, typically it's much larger, like 200, 250, 300 meters. And simultaneously, the same radar can also offer a very broad field of view up to typically 150 degrees. So this is one requirement which should be fulfilled. And there you have detection ranges 50 to hopefully 70 meters. Now, what are the typical sensor configurations? Well, the traditional sensor configuration, I would say, is that you have a single front radar, which has detection range up to 250 meters for your adaptive cruise control. Of course, therefore, you need a focused beam to get enough energy into this direction here. And the same radar has a broad field of view, for instance, for urban scenarios or emergency brake in urban scenarios. And for instance, Mercedes-Benz E-Class, you could also have two rear corner radars, which are used for lane change assist on the highway, where you typically have a focused 80-meter range beam, and the same radar has a broad field of view for blind spot detection. Now in the future, what will be the main change? Will typically, the first one is that you offer a full 360-degree radar cocoon around the car, so a seamlessly environmental sensing from 50 up to 70 meters, I would say, using at least 4 corner radars, so 2 in the rear, 2 in the front. If you have a relatively long car, then maybe also 2 in the B pillars. And then the rear corner radars typically have to increase the detection range up to 160 meters. This is unnecessary for advanced, let's say, autonomous lane change features. And of course, we see more and more performance in the single front corner radar, which you need for high performance adaptive cruise control. Okay, so we will see more and more radars in the cars. So this is typically also setups going into modern designs. And of course, we also see more and more radar for comfort and safety features like inner gesture control or let's say vital monitoring and sensing of the driver, or if there are children left in the car, seat occupancy detection, or tailgate opening. So this is all technology where you also see radars in modern cars. Now, the particular challenge of automotive radar is, I mean, it's a nice situation if you are working in that field, because we do have pretty large market volumes, around 100 million devices maybe today. But from this, of course, results that it is really a high volume product. I would say the automotive radar market is the biggest market for millimeter wave components today. So they really must be cost optimized. So you have to get this compromise between high performance and low cost system right, okay? Which means typically we do have limited processing power, maybe just 1 megabyte of RAM for storing the radar data. Typically you do not have the large possibilities to calibrate your device once it is deployed, because the car manufacturers get the radar, they just clip it behind the bumper at the manufacturing line. You have some mounting tolerances there, and then basically your radar has to work out of the box, okay, without precise calibration. This is why you put a lot of effort into like auto calibration algorithms, which means while you are driving, the radars, for instance, automatically calibrate themselves to get the direction of arrival estimations and algorithms precisely to update their models on the impairments due to the bumper or mounting tolerances. Then you have to be robust towards, ice, snow, and mud, and of course you typically do not have any maintenance during lifetime. So lifetime is maybe like 15 to 20 years, and during that typically you do not have regular radar calibration intervals. And due to this also, let's say from a market perspective, the automotive radar market also is not too much into revolutions, but for the automotive customers it's very important that the systems you offer, they are mature, okay, so that you basically have established processes, and this is why you typically need a large company and you can cope with all of those challenges here. But now the question, of course, is for us as engineers, maybe you're most interested in how do the radar sensors internals look like? So how do we build an automotive radar sensor? So since it must be a cost optimized product, of course, the design paradigm is keep it as simple as possible, as cheap as possible. So we typically just use one PCB. The front layer, we do have an RF substrate, because there you do have your RF, your antennas, printed antennas, feed lines, and then your radar front end. And then typically on the back side, it's just an FR4 PCB here on the back side. You do have all the, let's say, circuitry which you need, for instance, for power supply and management, signal processor and everything, which is digital. And then you have a connector here, and you go to the vehicle bus system. So from a functional point of view, you just have 5 functional blocks. So we do have the antennas and RF passives here, like balloons and feed lines. Then we do have a radar front end, which typically is a fully integrated radar MMIC today. a signal processor, which just has a digital interface to your radar front end, and then from that signal processor you directly interface using some bus drivers with the automotive bus system, which either is a CAN network or automotive Ethernet. And then you take this PCB, you put it on aluminum housing to get the heat away. You apply some shielding above the MMIC and the balloons and feed lines to shield from parasitic radiation, and then you seal it in a plastic radome and housing. Okay, and that's basically how you produce such a radar sensor. Then the question is, so how does the antenna layout typically look like? So modern radars typically do have 3 transmit and 4 receive channels, so we will see some more details on this later. And with this pool of transmit receive antennas, basically you have to cover different application requirements, which is you typically need focused beams for your long range detection, for instance here shown to the rear for this lane change assistant, and simultaneously you need those broad beams for like blind spot detection. You always want to shape the beam in elevation because you do not want to radiate to the ground, neither to the sky. And for that reason, you always use long antennas in the vertical plane, because if an antenna is long in one dimension, then it focuses the beam in that direction, okay? So we use those long branches to focus the radiation into just the horizontal plane where we want it. And then basically you can play with the different vertical configuration of your antennas to realize those different beams. And typically you realize such a narrow beam using a large aperture in the azimuth plane for the transmit antenna only, and the RX antennas, you see we have 4 RX channels, so 4 independent RX branches. They are single branch antennas, so that they do have this broad beam. So RX is multifunctional, always broad beam, and with the transmit antennas you realize those different azimuth beams. Okay, traditional configuration was vertically polarized patch antenna arrays, series fed. Very nice technology, has very nice properties because the mutual coupling, especially between your receive paths, is reduced, which means you do have less ripples on the azimuth and phase pattern, which is very nice. You do not need much calibration here for precise direction of arrival estimation. But the vertical polarized patch antennas do have one problem, which is you cannot realize this extremely broad azimuth field of view, because the single vertically polarized patch antenna on the ground plane does have zeros at plus minus 90 degrees of azimuth, which reduces your overall pattern. And that's the reason why today more and more radars use horizontal polarization, because there you can more easily realize this broad azimuth patterns. But the drawback is that the mutual coupling now between your individual branches is a bit larger, so the technology is a bit, let's say, not so easy to behave or to control. Now we had the antennas. Now let's look at the front end, which we need basically to interface using the antennas with the channels. So we are using FMCW radar today, which means what we need is a synthesizer. Then we need a couple of transmit channels. Those transmit channels, of course, do have power amplifiers, but they also do have relatively fast switches and phase shifters, which we basically use to impose an additional modulation on the radar waveforms dependent on the channels, which you need to orthogonalize the transmit waveforms if you want to do MIMO radar. We will come to this later. And then we do have our typically 4 receive channels where we amplify the received waveforms using a low noise amplifier. Then you downmix the received waveforms with the transmit signal according to the FMCW principle. We will also see this in one of the next slides, into baseband. Then you have your baseband amplifier, bandpass filter. Then you digitize the received signals, and then you have the A to D converters, and you just have a digital stream to your microcontroller, a signal processor, or it was also FPGAs a couple of sensor generations ago, but today it's just the automotive radar signal processors. Now if you want to build such a front end, of course you do have different integration levels. I mean, you can get for all those functional building blocks also different components, like get isolated transmitters, different receivers, a different synthesizer, a separate microcontroller unit, and hook this all together, and then you can build a radar system. Benefit here is you are very flexible, so you can easily do like 3, 4, 5, 6, 7 transmit channels and multiple receive channels, and play around with PLL characteristics. But of course, you have to route a lot of, let's say, RF signals on your PCB, and the whole setup is not, let's say, the most cost optimized one. So the typical setup today is that you get a fully integrated transceivers having all those components on board, including the data converters, 3 transmit channels, 4 receive channels typically, and then you just digitally connect your microcontroller unit with a high-speed streaming interface for the received data and an SPI interface to basically control the modulation parameters and all your transmit and receive channel parameters. And those front ends, the fully integrated transceivers, also do have local oscillator outputs because this and inputs, because this allows you to cascade those transceivers. For instance, if you use 2 transceivers, you can build a 6 transmit, 8 receive channel radar system and improve the performance. The next integration level is the single chip radar. So take your signal processor and your, let's say, transceiver front end and combine this into a single package, which makes basically your radar even maybe more cost optimized. Challenge here is that these are the 2 hottest components. They consume most of the power. You put them in one package, which makes thermal design not an easy task here. And of course, it's not also too easy to get high performance computing power into here. And finally, the next integration level is the antenna and package radar. So you also take the antennas, put them into the package. This is very attractive because then you do not have to route any RF signals on your PCB, which means basically you can use an FR4 only PCB, so you do not need any high frequency laminate. And PCB cost is typically one major factor in your bill of materials. So this is very attractive also from a price optimization point of view. But the challenge here is, of course, you only do have a very little antenna aperture. You cannot play around with your antenna layout. So basically, it's a bit limited to near field or low short range applications. And finally, we can look at the signal processor, which is, I think, also very important to look at this one if you talk about automotive radar, because typically today you could think, well, computational power in today's time is not an issue anymore, but it is for automotive radar. Because due to our cost optimization, and since we need signal processors which are rated and certified for automotive use, processing power is limited. And it is limited in such a way that the processing power we do have also limits the performance of the radar, which means if I had more memory and a bigger processor, I could easily improve the performance of the radar, for instance, in terms of detection range or angular resolution, without changing the RF frontend. Okay, so it's very important. Computational power is a performance limiting factor in today's radar systems. Yeah, and here's just short, let's say, overview. Typically, we do have like 1 to 2 megabyte of RAM to store the radar data. So I told you we do a measurement every 50 milliseconds. So in the measurement, you store maybe collect 1 megabyte of radar data, receive data, and then you have to process within those 50 milliseconds so that you can free that memory for the next measurement after 50 milliseconds, that the memory is available again. Within this cycle, you have to do all the processing. And therefore, we do have also some dedicated signal processing units, dedicated hardware acceleration. Very important is some hardware to the FFT. We will see this later. Yeah, but it's still a performance limiting factor. Then you could also think about, well, why not stream all the data to one of those centralized high performance GPU nodes? Well, of course, there's some, let's say, architectural arguments then that maybe your customer doesn't want to do this, but you are also limited to the data rate which is offered by typically automotive vehicular networks, which you have today. And the fastest one which we have is Automotive Ethernet, which can basically deliver 100 megabits over an unshielded twisted pair wire. And if you compare the typical data rate of a single radar measurement with the data rate which is offered by the fastest automotive network system, you see that you also cannot just stream out the raw data from your radar sensor to some centralized node so easily. Yeah, and now let's get a bit into a signal processing view. So basically, when we interact with the channel, then it is a very long way from our received signals to the vehicle interface. And here's kind of a top level overview what's going on in the radar sensor. Because so you receive the data and you digitize it, you send it to your signal processor here. And then of course you first do some ADC data pre-processing, some conditioning, some monitoring if you have clipping due to large transmit and receive amplifier settings, which then would lead to that maybe you adapt your modulation and amplifier settings. Once you have then the ADC data in memory, you do the 2D frequency estimation. So you apply this 2D FFT. And then from those 2D FFTs, you do the detection and simultaneously kind of the direction of arrival estimation, which means you have a point cloud here at this stage. Now, then you apply a tracker on that point cloud. So basically an algorithm which analyzes those point clouds and really checks, okay, where I have a car, a truck, also does classification and so forth. And finally, you could also have a function directly on the sensor, which basically analyzes where we do have objects and then decides if, for example, the warning light in your rear mirror has to light up. And then on the vehicle CAN bus, for instance, the radar sensor just emits the signal, please light up the warning light in the rear mirror. So this is possible, and this is done in a lot of sensors today, that we do everything up to the function. Quite often the function also is a software component which is supplied by your customer. So you have to provide some free space in your application that your customer can implement the function. But what we also do have is a virtual multiplexer, which means basically we can route out data from any of those domains. We can also send out just the objects. So where is a car, where is a truck, where is a pedestrian? To a centralized node in the car. We can also send out the point clouds, or we could send out the 2D FFTs or even the raw data. Of course, if the speed of this interface here allows to. But then the radars also receive data from the car and from other sensors. First of all, we receive vehicle data, which is necessary for the sensors basically to estimate the state of the system. So basically the driving direction. So we need the automotive data like speed and steering wheel, especially for tracking. Okay, so to distinguish what of the targets we detect are basically static, so not moving with respect to the environment, and which are dynamic objects like pedestrians, cars, bicycles. And we can also receive data from other radar sensors, and this typically is used for sensor data fusion. So you receive the point cloud from another sensor. So you do a data fusion of your own measurement, your own point cloud and the point cloud of the other sensor before doing tracking on the data fusion point clouds. Okay, so this is also possible. And if you talk about distributed processing, which means this typically means that all the sensors do processing up to a very, let's say, high level. And centralized processing would mean the sensor basically is just a data collection device, and then you send out this data and you have a high performance GPU platform which does all the tracking, maybe together with information from cameras. And now on this slide, basically, I just have a visual impression on how this data looks like. So scenario is a typically driving scenario on a German road. Here we do have the rear right sensor. This is the rear left sensor. So I'm not interchanging left and right, but it's just because we're looking to the back of the car. And here you can see the FFT outputs from both radar sensors. Here's the point cloud, 0 to 200 meters to the back. And here's basically the detected objects. You can see how all those other traffic participants basically map to point clouds. We do have two different colors for the two different radars, and then how the tracker basically get rid of all, let's say, additional radar detections we have, and just keeps the true objects which we have. What is also very characteristic in those raw target FFT output here is those parabola-like shapes which we had. And basically those shapes is, if I play back this again, is your road boundaries, okay? Because from the road boundaries, which are very near to your car, you just basically those boundaries just have tangential velocity. And of course, tangential velocity does not create Doppler. So they appear at short range 0 Doppler. And the road boundary components far away do have a lot of radial components. So basically they create a lot of speed here in that image. And basically, if you take the tangent here at this parabola-like shape, then this is your ego speed, the speed you are driving at. And this is how, for instance, you can also measure your own driving speed with the radar system. Now, I told you that this tracker here basically analyzes the point clouds which we have after detection and creates boxes where the radar is sure that there is a moving and dynamic object. And of course, the question now is if we can distinguish between, okay, I have to move this video, if we can distinguish between moving and static objects, then the question is, what can we do with the remaining objects? So what can we do with all the detections which are static with respect to the environment? And this is what you can see here. Those targets can be used to build a map based on radar. And this is also necessary today to implement some functions, for instance, for autonomous valet parking, because you, of course, want to use the radar sensors to detect parking spots. And just to give you an impression how precise we have to do this, one requirement from the car manufacturers today also is that you can measure the height of the curbstones with the radar, okay? One reason, for instance, is that at least in Germany, it is not allowed to park in front of a lowered curbstone because there typically another street enters your street. And this, of course, must be able to be detected with your radar systems. Okay. And of course, yeah, then a function applied on this would be that then you analyze those radar-based maps. And from that, you can generate something similar to those dynamic objects, which we call fences interface. So you basically determine where is an area where you can drive to or where are potential parking spots, and then you can output this information to a centralized node in the car. Okay, now I think you should have a good overview impression. Now the big question is, how does it work? So what are the operating principles of automotive radar? Now, we had talked about radar in a nutshell, that we emit an electromagnetic waveform. We also talked about that we do this at 77, 76 or 79 gigahertz frequency bands. But now the question, of course, is what is the shape of this waveform? If you do radar, you typically do have a lot of options in selecting a radar waveforms. Very intuitive, of course, is the pulse waveform. So send out a short pulse, wait until the echo returns, count the time between those pulses, and you have the range. And there's then a lot of intermediate waveforms which are of particular use, especially in industrial radars. But today we use frequency modulated continuous wave in the radars, or also Chirp-Sequence radar. So we use basically continuous wave signals which linearly increase their frequency. So this is today's automotive waveform. So any radar on the market uses the waveform. Potential new waveforms are OFDM radars, pseudo-random radars. They do have some drawbacks and also some benefits. We will come to this later, but now, first of all, let's look at what we use today and also in the next couple of years, I would say, which is FMCW radar. So how does FMCW radar basically work? So your transmitted signal, shown here in blue, is a continuous wave signal, which linearly increases its frequency. So maybe we start at 76 gigahertz, and then within the chirp duration, which is a fraction of milliseconds, we increase the frequency to 77 gigahertz. Okay, so this is the instantaneous frequency versus time. Now we send out this waveform, it propagates through space, hits a target, returns. So what we receive, shown here in red, is a delayed and attenuated copy, right? Now let's look at the instantaneous frequency plot. So basically the instantaneous frequency of the return signal is shown here. And now the particular property of FMCW is the following. Since we do have a linear increase of frequency or momentary frequency with time, we see that the frequency difference between received and transmitted ramp is constant, right? Okay, and this frequency difference is also just dependent on the propagation delay TD and the slope of your ramp, which means if we can measure this frequency difference, we can calculate back to the propagation duration, and from the propagation duration, we can basically calculate back to the range. Now the question is, how do we measure this instantaneous frequency? Well, we just measure that by multiplying blue and red signal here in the mixer, and then filtering the mixing product, so basically filtering out the sum component oscillating at more than 100 gigahertz, so that just this IF frequency, so the difference frequency component here remains. So what we have here at the output is a cosine oscillating at this different frequency. So digitize that cosine for a certain duration of time, do an FFT, you have a single peak at exactly the frequency which corresponds to the range of your target. So that's the fundamental principle of FMCW. Now, there is a challenge, because if the target also is moving, we not only get this shift in horizontal domain, but also in the vertical due to the Doppler. But then you do have a problem if you just use a single ramp, because we have one measurement, this IF frequency, but two unknowns, the speed, so the Doppler frequency respectively, and the range. And this cannot, of course, be uniquely resolve the situation. For resolving this situation, you either need multiple linear independent measurements using different ramp slopes, or as we do today, we use a Chirp-Sequence radar, which means instead of using a single relatively long, slow ramp, we use in the same duration of time a lot of shorter ramps, maybe 128 ramps. And then basically we organize the output here in a certain manner because we organize it in a matrix. So how does it work? So the received signal from the first chirp goes into the first column of a matrix. So here are all the samples of the first received chirp. And then the second received chirp goes into the second column and so forth until we filled all of our matrix. So for instance, we do have 128 chirps, so 128 columns, and maybe 256 samples per chirp, so 256 rows. Then the rows are called, for instance, the fast time, because here we do have a relatively fast sampling period, and the columns are called slow time because from column to column we do have a relatively long observation period, because this corresponds to jumping from chirp to chirp. And then basically, of course, if you select the modulation correctly, you can go from this precise formulation, how the phase behaves in this column, to some simplification, and you see the following. Now, if we walk along K, the fast time, you see that the frequency along the fast time is only dependent on the range. And if you walk along L, the columns here, we see that the frequency component is only dependent on the radial velocity. So basically it's the Doppler component. So what we did now basically is to separate range and Doppler effect into two orthogonal components. Okay. And then we do have to estimate the frequency along those two orthogonal components along fast time and slow time, which means we need a two-dimensional Fourier transform. So this is why we also want to have this 2D FFT accelerator, because in hardware, because this algorithmic step has to be done in every FMCW radar system using a Chirp-Sequence approach. So for instance, if we have a single target which moves at a certain velocity, then the data matrix would look like this. So fast time here, slow time here, you see that the target is moving because all those equal phase parts are tilted with respect to the slow time. If the target would not be moving, they would be parallel to the slow time here. And then we do the 2D FFT, for instance. First, we do the FFT along the fast time, which transforms fast time axis into range axis. And basically it collects the energy, all the energy distributed here in the matrix into the corresponding range bin of the target. And then you do the second FFT along the slow time, and you get a single peak in this range. Now range velocity matrix, because the second FFT transforms slow time into Doppler basically. And you just have to detect the single peak, read out range Doppler, and basically you have range Doppler information of your target. And this is exactly the magnitude of this is exactly the RV image which we have seen. And it's also very important to understand that radar or FMCW radar, or most of basically all coherent radars, are very sensitive regarding resolution in this velocity domain. Which means if you have a radar and nothing is moving, what do you have then? Then you do have all the target responses on the zero Doppler component. And basically you do not utilize this whole plane for separating the targets. But as soon as the targets move, or maybe also you move, you basically use this pretty good velocity resolution of the radar to resolve all those targets in range and velocity. So it's very important that those radars need some movement. So they are not good if nothing is moving. So a particular challenge, for instance, is parking applications where nothing is moving, because then you basically cannot utilize the velocity properties of your radar. Some performance formulas are just condensed here. Well, range resolution. So basically, What does resolution mean? In terms of radar, resolution always means what is the closest, let's say, distance of two targets in your respective resolution domain, which could be range, Doppler, azimuth, or elevation, that you see those two targets. Because if two targets, let's look at the resolution and range, if two targets are too close together, then you just see a single peak in your FFT. Basically, you just see a single target. And at a certain distance, the single peak occurs at two peaks and you can resolve the targets. Now in range, this resolution just depends on the bandwidth you use. And this is why we are interested in those large bandwidths like 1 gigahertz or even 4 gigahertz of sweep bandwidth. Because with, for instance, 800 megahertz of sweep bandwidth, you have a resolution, range resolution of about 18 centimeters. Okay. And this is also the most important benefit of FMCW radar, because with FMCW radar, basically we can use gigahertz of bandwidth to get a very nice range resolution, but we just have to sample and also process the data at this low IF bandwidth, at this difference frequency. And this is typically limited to maybe 1 megahertz or something like this. So we get gigahertz performance in terms of range resolution for the cost of megahertz sampling and processing. And this is also the big drawback of like OFDM or pseudo-random radars, because they, of course, do have the same performance resolution, because this formula basically is the same for any radar waveform. But in OFDM or pseudo-random radars, they typically also do have to process at the gigahertz rate, which means you need high-speed A to D converters, but this is just one piece what you have to fulfill, but you also need big memories and faster algorithms. Now, what are some advanced things which typically you are working on today in automotive radar? And the biggest thing, or the hottest topic most of the developments are focused at, is going from radar to imaging radar. So everything which has to do with direction of arrival estimation. So getting angular resolution, and of course using the MIMO radar approach. Now, if you also want to measure the angle of targets, then a single transmit and receive antenna is not enough, because we need spatial information, which means so we kind of have to spatially sample the impinging wave field with multiple sensors. So we at least need multiple receive channels. They all basically look the same, just multiple coherent receive channels where we do have the antennas placed at a certain configuration, maybe a uniform linear array, also some sparse arrays. And then our basis where we are processing with, it's not the range Doppler matrix anymore, so slow time, fast time matrix anymore, but we do have, if we have 4 receive channels, we do have 4 of those matrices, which means basically we do have now the radar data cube with the dimensions, fast time, slow time per channel, and of course the antenna channel. Okay, and this is now the basis. This is what we have to store in memory and then to process to basically create the point cloud out of this, right? Now, traditional direction of arrival estimation is very simple. So you just look at kind of the range velocity image. You look at the peak. So at one peak of a target, maybe at a range of 10 meters and a certain velocity, you read out the complex values from all of the other antennas, and then basically you can do something like a phase monopoles. So look at the phase differences between your channels and map those phase differences back to the angle of the target. So this is an algorithm which I would say is running in most of the also modern radars, although it is a World War II basically approach today, because it's very simple and you can do this for all the detections within your measurement cycles. But the problem here is it measures the angle of the target, but it has no resolution in angular dimension. So what does this mean? Basically, if this algorithm sees a peak here, then it assumes that it also is a single target. But this peak basically could emerge from 2 targets, because if you have 2 targets at the same range, let's say I'm the radar, so my arms are the range, the targets are at the same range, they are not moving, but at a different angle. Then of course I just see a single peak here, but there's 2 targets in that single peak. And this algorithm would just output one angle, one target, but of course that angle would be completely wrong. So if the targets are equally strong, then maybe the algorithm just outputs the mean angle, for instance. So it does not resolve an angle, okay, but we need those resolution and angle, maybe at a parking situation, so velocity is 0, and of course we have to monitor the environment, so what are the cars around us, maybe if two targets at the same speed are following us, also if you have specular multipath reflections, and typically we want to resolve, so that's not the ultimate criterion, so maybe for mid-range radar, something like 4 degrees in azimuth resolution for today's development is, I would say, is pretty good. But of course, in the future, you should go below 1 degree. So the typical toolbox, you can take this from signal processing, also from communications, ranges from algorithm, basically, which do offer spatial resolution from, of course, beamforming to like high resolution algorithms like music or Esprit, and today, of course, even compressive sensing or maximum likelihood estimation. But in radar, we do have some particular problems, which is all the signals we have to separate are coherent. So this is one challenge, which is not very nice. And we also do have one snapshot. And this is the particular challenge, especially compared to communications, because in communications, if you have two mobile users, then typically you can observe them for a certain time. So you can collect multiple snapshots. And then, of course, the data coming from those two users, you want to separate an angle, also is typically statistically independent. And then you have uncorrelated signals. But in automotive radar, we just observe for one snapshot and they are correlated. So which renders a lot of those approaches not too attractive, and basically remains that maximum likelihood is very attractive. But now the question is, why is it so hard basically to make a picture with a radar compared to the camera? And the problem is especially shown here, because a radar sensor can be regarded very similar basically to what is done with the camera, because what does the camera do? So the camera does have a sensor screen, and we do have an aperture here, and maybe we do have 2 point sources in space. So we want to make a picture of those 2 point sources. And what we see on the camera's screen is the Fourier transform of the electromagnetic wave field here at the aperture of the camera. Because if we do have an optical lens, then this basically is nothing else than a Fourier transform. I mean, a lens does a Fourier transform. So the picture we see is the Fourier transform of the wave field in the aperture. Now, cameras are also subject to the same resolution limit as the radar is, which is the so-called diffraction limit, because we do not see the ideal point response here on the sensor screen, but of course the energy is smeared on the sensor screen due to the finite aperture size, which means that if those optical point sources are too close together, the individual peaks basically smear together, they add up into a single peak, and then no matter how many megapixels your camera has, you will always see just a single peak, and this is the so-called diffraction limit. And we can make pictures with cameras because the aperture size here compared to the wavelength is a couple of thousand wavelengths, because the optical wavelength is so short. Now, if you have a typical radar, which has an aperture size of maybe like 2.5 lambda, then you get a rather large diffraction limit, which means compared to the camera, where the 2 point sources can be in the sub-degree range spacing, and we stick at this, we get this high resolution image. In a radar, the physical diffraction limit is so large that basically the targets had to be spaced like 20 or 30 or 40 degrees that we can resolve them. And of course, this is not sufficient if we talk about this 1 or 4 degrees. So radar has to beat physics somehow, and we have to typically beat physics using those super resolution direction of arrival estimation algorithms, under the constraint having single snapshot and coherent targets, which makes it very, very complicated. And this is why the typical workflow today looks like this. So one of the most, let's say, attractive algorithms is really a maximum likelihood search, which is computational very, very demanding. And therefore, typically you do the following. So you do this very simple phase monopoles for all of the targets you detect during one measurement. And then you take this initial angle for all of those targets, assuming that it's just one target, and you apply a very fast model order test on those peaks, and you check basically, is it just one target, or maybe is there multiple targets hiding in this single range velocity peak? And quite often this test says, well, there's just one target, and this basically means you are done, and only for a subset of targets you have to apply this maximum likelihood techniques, which then brings you maybe to a resolution, a factor 2 to 3 below your physical resolution limit. So with this, having a 4 receive antenna uniform antenna array, you maybe get a 15-degree resolution in azimuth, which is also not yet sufficient. So the question is, how can we go down to those 4 degrees, and therefore we have to increase our aperture to also improve this physical diffraction limit. But we cannot just spend more receive channels, because then the radar gets bulky. We need more receive channels, so it gets more costly, whatever. So this is why typically today, if you need this, you apply MIMO radar. And what is MIMO radar? MIMO radar basically says that if you have multiple transmit channels, so you also do have spatially separate, let's say, points where you send your probing signal from, and you can separate those signals in the receiver again, then you can create from such a real antenna configuration, a 4-element uniform receive antenna array and 3 transmit antennas, a virtual receive antenna array, which basically has 12 antennas. And the virtual configuration is copy and pasting this receive antenna layout on your transmit antenna positions. And this allows you to easily span a large, let's say, azimuth aperture, but it also allows you to span an elevation aperture quite easily, which you need for elevation direction of arrival estimation, because you cannot easily span an elevation aperture using the receive antennas alone, because they are very long in elevation, which we need for elevation focusing. But of course, therefore, you need to create orthogonal transmit signals, and this is the reason why we do have this phase shifters and the switches in the transmit channels. And MIMO modulations typically used today are either time division multiplexing, so you distribute the chirps among different transmit antennas, and then basically you can easily separate the signals in the receivers again, or you use a slow time phase code. So one transmitter transmits at 0-degree phase, and the other one basically shifts the chirp by 180 degrees each transmission, and then basically it kind of results in that you shift static targets from the second transmit antenna into the Doppler domain, and then you can basically split your range velocity image in half and separate the signals from the transmit antennas. But in both cases, a MIMO always is a trade-off, and this is also very important to understand if you are maybe working in the MIMO field, since we basically processing power is limited by the number of elements in this radar data cube, how much we get into memory, which means if you collect more information spatially, then you always have to sacrifice under this constraint that the total amount of data points is limited. You always have to sacrifice either range or velocity. Okay, which means you cannot just multiply the performance of your radar using MIMO, because you have to trade off somewhere. Or in this case, you could switch on then 2 PAs at the same time, but typically then you run into heat problems because you cannot really switch on 2 PAs at the same time, because also with 1 PA you are running at the thermal limit typically of your radar. So this is very important to understand. MIMO always is a trade-off, not a win-win situation. So you have to think about, okay, when do you apply a modulation which uses MIMO? Maybe for parking, because you do not need this high velocity properties here. Now let's have a look at some future aspects before actually concluding the talk. So there's a lot of future topics, and today I'll just have a small selection. Interference, scaling up MIMO, novel waveforms, AI, machine learning, cooperation, and so forth. So maybe we just dive into those a bit, that you get an impression on that. Of course, I told you we will see many radars in the cars, 4 to maybe 7 radars per car, and basically every car will have a lot of radars in the future. So since radar is an active sensing technology, we will see interference. So the problem is what happens with basically when we are sensing using radar and we have this interference. Well, first of all, FMCW already has some inherent robustness towards interference, because first of all, we are measuring in a relatively small duty cycle. So we said every 50 milliseconds we do a measurement, but one Chirp-Sequence measurement just lasts a couple of milliseconds. So there is a certain probability that the other cars do measure basically when we are not measuring. So this is the first robustness. Second robustness is that the receiver bandwidth is just a couple of megahertz compared to this extremely large RF bandwidth, which is 1 gigahertz or maybe even above, which means if you see interference from another radar, basically you see a ramp crossing. And which means the signal from the other radar crosses your IF bandwidth just for a short period of time, which basically gives you just a short peak in the time domain. And then what you do with this corrupt received data is basically that you detect this large peak, you remove the corrupt samples, and you interpolate over it. And this is also what you do today, together with, of course, adaptive strategies like listen before talk, adjust your transmit timing, adjust your transmit frequency, try to characterize what other radars are transmitting, and adapt your measurement strategy to the other radars which you are seeing. And then, of course, to mitigate and avoid those interference phenomena. This is good for today, but of course challenging for the future. If you would assume that in every chirp measurement you have like 20 peaks, then of course we are running into a problem, because the information then would be gone. Yeah, if it looks like this. So this still is an open challenge, and I have not yet seen any solution to that. Then, of course, some future aspects is also signal analysis. So this is what we were interested in. Of course, you quite often also want to use the radars in the car to really visualize what's going on in the air around you, to really evaluate basically what are interference scenarios. This is also the way towards cooperation, passive radar, and so on. And of course, the engineer's dream would be a setup like this. So put a lot of high performance spectrum analyzers in your test vehicle that you can drive around and basically monitor what's going on in the air to implement like cognitive and adaptive strategies for avoiding interference and so on. But of course, you cannot go to your manager and say, well, I need a couple of those measurement devices in my car. I think your manager would not be too happy with this one. But we recognize, well, basically we do have multi-channel spectrum analyzers in our test vehicles, because if we have a test vehicle which has a setup like this, where we do have 4 radars in the corners, each radar has 4 receive channels, then basically we do have 16 spectrum analyzer channels. Why? Because if you look at the receive path of a radar system only and compare it with the typical spectrum analyzer, then you see your radar basically is a spectrum analyzer, okay? And this led us to the approach that basically we reprogram the radar sensors in our test vehicles so that they act as time frequency analyzers. And then we were able to basically drive around and monitor what's going around in the air in real time, basically around our car. For instance, here you see recordings of Bosch radars, which were mounted in Volkswagen Golf cars typically. Here you can also see that they are using not a Chirp-Sequence radar, but a slow chirp waveform, because to resolve this range Doppler ambiguity, they are using slopes or ramps with different slopes, for instance. And we were also able to characterize multi-car scenarios. So you have car 2 radar signal, car 1 radar signal, and here a very fast chirp high performance radar system. And of course, yeah, we also did implement this in real time, which means if we are driving on the street and we just activate a single receive channel here, and then you go into front of one of those radars, you see basically in real time, you can observe what's going on in the air just using the radar systems. Then, of course, in the future, scaling up MAMO radar is of recent interest. So really improve your aperture, use more transmit and receive channels. Therefore, we can make use of those local oscillator outputs and inputs to maybe have a 6 transmit and 8 receive radar configuration, or even go to a 3 MMIC setup where you could have 9 transmit and 12 receive antennas, which gives you at maximum 108 virtual receive antennas. And if you go through the recent papers, you also see announcement like more than 500 virtual receive channels. So this could be the future vision, for instance. But one challenge here is not only just to realize the system, but what you need for MIMO is this orthogonality between the FMCW radar channels, which means, yeah, this will be hard with FMCW waveforms to get this orthogonality. Novel waveforms also is one aspect, but as I mentioned, the nice thing of FMCW today is that we do get the gigahertz performance already at processing of just speeds of just megahertz. So this is very attractive. Of course, we just have limited waveform flexibility here because we are sweeping through the bands. but therefore it is very cost effective. And in the future, of course, we want to have more waveform flexibility to be able to scale up memory radar systems, have more degrees of freedom to get this orthogonality, to handle interference, and also to introduce communication over radar. But therefore, all new waveforms like OFDM, pseudo-random radars do offer full waveform flexibility, but you get the same gigahertz performance for range resolution in terms of gigahertz cost, which means you need a full band receiver. And yeah, since I think I'm about the end of this talk, so a 1 hour talk, so I should stop here. Just a short overview on artificial intelligence. Of course, we do a lot of machine learning today in the radars. First of all, to classify objects, like to really know if one of those point clouds is a pedestrian, is a truck or a car, to classify what interference we see. And my personal interest is, yeah, basically to use machine learning for high resolution direction of arrival estimation, where we had a lot of publications in the last couple of years, basically how you can train artificial neural networks to implement this full super resolution direction of arrival estimation workflow using relatively simple feed-forward neural networks. And we had some very interesting results here, how you really can implement fast super resolution direction of arrival estimation for multiple targets using feed-forward neural networks. I will skip this part on radar cooperation. Basically, there's a couple of other talks from me online which go into a bit more detail into wireless synchronization and radar cooperation. Basically, we were able to reprogram radar sensors such that they kind of are able to wirelessly synchronize on other radars, and then basically we can de-chirp, as shown here, the signals from a completely black box other radar sensor signal into our own baseband. So I would like to conclude my talk with this outlook on future ideas. I would like to thank you for your attention. Of course, in the full deck of slides, you find a lot of references and a more extensive treatment on that material. But for today, I would say we had a look on enough material. So thanks for your attention. And then I would like to hand over to my host again. So thanks.
Thank you very much, Professor Markus. I think it's a really interesting talk. So I have a few questions lined up. I will ask questions one by one. The first question is, can LRR for ACC be used in railway application for obstacle detection? What modification would be required in any commercial products available?
Okay, so for which detection?
For obstacle detection in railway.
For obstacle detection in railways, so we do have, so as I told you, so Innocent also does have an industrial branch, and basically here we are deploying systems for railway use. The systems basically, yeah, typically in railway applications, most of the customers are not really interested in obstacle detections. Most of them are interested in true over ground speed measurements. But if you would like to implement obstacle detection as you do it in the regular radar, then I would say in the automotive radar, there's not too much changes basically you have to apply. I mean, maybe you have to, of course, modify your tracking algorithms or the models, because typically you are not expecting some, let's say, pedestrians driving next to your train like you have in urban scenarios in the cars. Of course, you should have to update all those models there, but of course it depends really on your application scenario. So I have not yet heard from regular obstacle detection, but should be not a problem, because the application scenario, I mean, driving speeds, whatever, are not too different from automotive use. I would say it's just a simplification basically of the automotive use, because in the railway application you just have this linear movement. So to conclude, basically you have to apply or simplify the models, but I would say it's a more simple use case. Yeah.
Yeah, very right. The other question was about the AI. I think you have already answered this question in the last few slides. The next question is autonomous vehicles concept is applicable to less developed countries like Pakistan or India?
Well, that's interesting. So unfortunately, yeah, due to Corona, I cannot visit Pakistan and get my personal impression from the traffic there. But I once visited Jakarta, Indonesia, and I think you are familiar with the traffic situation in Jakarta, which is a very challenging one. And I was talking to my host there, and I kind of yeah, joked with him that in my opinion, in the traffic in Jakarta, an autonomous vehicle would just do one thing: it would stop and not drive anymore. Because typically the first fully autonomous functions will be very defensive. Okay, so you typically, of course, always, the autonomous car will always keep to the safety margins necessary and so forth. So if you have a lot of dense traffic, maybe with aggressive drivers, then I would say this would be very hard for autonomous cars. But really, more or less, I would say, depends on the traffic conditions. And if you have, of course, less denser traffic, then it's more simple to implement this. And this is also the reason why fully autonomous urban driving is much more challenging, of course, than fully autonomous driving on a highway. Because on a highway, at least in the European highways, typically the traffic is not so dense and the environment is much more controlled. So if you have traffic scenarios where you do have a lot of unknown factors which are not too controlled, then of course it's very challenging. But I think in the future, of course, it should be applicable to also countries where we do have some traffic challenges today.
Yes, you are very right. I guess the dimension of the problem become much higher if we talk about the scenarios, and there are a lot of unpredictable parameters that you have to consider while applying there. Yeah. The next question is how the compressive sensing can be utilized for this kind of framework. What are the possible trade-offs as compared to this classical approach?
Okay, yeah, so first of all, let's say from a research perspective, compressive sensing is has a relatively high interest because you can easily apply that, or it's perfectly suited for sparse arrays. Quite often today, I talked about we use the RX antenna layout, or the MIMO layout has some uniformity, some uniform linear array layout, but of course this is not the optimum approach to cover a large aperture with just a low number of receive channels. So typically you apply a sparse aperture, and therefore compressed sensing is quite attractive. What is a problem in compressive sensing with regard to a series application is this iterative solution of the problem, that basically you do not exactly know when you reach that goal, when you reach your optimization goal, because compressive sensing is always based on a kind of optimization. And of course, at least for series applications, you want to have very predictable algorithms where you know in which time you get which performance. And this, I would say, is one challenge in compressive sensing today. Yeah. And of course, together with the still very high computational load.
Yeah, that's correct. The next question is for applications like trunk opening, vital signs monitoring, seat occupancy, etc. Is 77 gigahertz is the choice of industry, or 60 gigahertz also being considered?
Yeah, typically, so for this use, then it's also the regulation aspects play some role here. For the use like trunk opening, you can also use like 24 gigahertz, because then it's not really an environmental radar working in the radar bands, because once you are driving, you switch off that function and you just use that function for if the car is standing still or parking. So there you can use those industrial, scientific, and medical bands at 24 gigahertz. Now for monitoring, interior monitoring, you typically, I'm not too deep into this one, but my last information is that you can use the 77 gigahertz or in the interior of your car for that. But you also see the trend that you get more and more automotive radar MMICs front ends from those big suppliers, with the same architecture, but with a front end tailored to the 60 gigahertz ISM band. So you typically see a lot of those functions then in the 60 gigahertz bands. Yeah, so this then is more attractive. Yeah.
Right. The next question is, what other hardware accelerators can be utilized beside 2D FT, that is wavelet transform, etc.?
Yeah, well, of course, this could be maybe realized. But what else hardware accelerators we have today? So typically you see one trend if you look at suppliers of automotive radar signal processors, that for instance, they also implement hardware-based constant false alarm rate detection and so forth. So more and more of those software algorithms go into dedicated hardware resources into the automotive radar signal processors. But this is a development which I see a bit with mixed feelings. I see this a bit critical, because especially the detection algorithms, there's a lot of empirical knowledge from the different sensor manufacturers in the detection algorithm that you get optimum detection for different scenarios. But now if you have a sensor or DSP manufacturer which puts a hardwired IP into the signal processor, then all the sensor manufacturers basically would rely on that same IP, and this I see a bit critical. So what I would see in the future is especially hardware accelerators, maybe for embedded processors like coprocessors, like small GPU coprocessors or neural network accelerators, where basically you still can make use of your custom IP, which was developed from a lot of, let's say, data you collected during the last years, but you have a general purpose accelerator to implement your specific algorithm. So this is the way I would go there.
Correct. The next question: are beamforming architectures using active phase shifters being considered for curved roads?
Yeah. So I think this question goes into if we use active phase shifters to implement beamforming in the transmit direction, right? I think this is the way this question goes, because I hear this quite often. Of course, this could be possible, but there you have some challenges. First of all, well, realizing all this, let's say, beamforming, you need some very typically fine granular phase shifters to really do this. And of course, this is a cost factor to implement this. But one other reason is this calibration issue. So if you want to do transmit beamforming, you need a precise phase distribution across your transmit antennas. But the problem is that due to some tolerances and this mounting behind the bumper, you kind of maybe have to adapt this to the conditions. And this precise phase distribution, so that the beamforming works as expected in the transmit direction, is much more challenging to get this calibrated compared to receive-only beamforming. Because in receive-only beamforming, you just have to kind of adapt your digital weights, right? And you can simply do this on the fly using adaptive algorithms and so forth. But also implementing this on the fly calibration in the transmit direction, you need the hardware resources like fine granular phase shifters which support this, but you also have to implement this calibration. This is not too easy. So therefore, of course, it could be of interest, but it's from a commercial or serious application perspective, it has some major challenges. Yeah.
That's correct. The next question regarding the interference. So in order to reduce the interference, can we employ communication techniques like OFDM or CDM, etc.? Yeah,
of course, there's a lot of approaches looking at handling interference using communication. And there's a lot of other, let's say, also approaches which realize a lot of interesting functions using car-to-car, car-to-X communication, or also communication over radar. The problem with communication always is that you need a communication partner. And this is the big challenge. This is basically also the whole challenge in autonomous driving. The situation would be much easier if you say, well, I have a technology which takes into account communication and I deploy this to all the cars around. But that's not the case. Typically, it's like you have a new technology, it goes into a couple of new cars, and then you have a couple of cars on the streets having this technology, and then during the years you get more and more cars on the streets having this technology, but you're still, even in 10 or 20 years, you will have some old cars which do not have these capabilities. And this is the problem with communication. You always need a communication partner. And the problem of interference, let's say, increases much more rapidly than you will see communication widely deployed across the cars. So this is the challenge with communications with a, let's say, real world commercial or market perspective.
Yeah, we have a couple of more questions. One question is how automotive radar can be employed or being employed in drone swarming, which is a very popular area of research nowadays around the world.
Yeah, I think I also do have some other talks on automotive radar where basically I focused more a bit on how we can use this automotive radar system architecture for other applications, because I see a trend like this due to this high market volume. Basically, those fully integrated radar front ends become more and more, so the price tag becomes lower and lower, and we also see those front ends now using the same architecture going into, for instance, 60 gigahertz bands. So I think this is very attractive because the standard system architecture which we have today for automotive radar can of course be directly applied to other applications like drone monitoring. So I think the platforms which we have in automotive is very attractive to really deploy this to other architectures or other applications, and then basically it's more or less just, I mean, it's just a software modification you need there. Yeah.
Yeah, that's true. The next question is regarding the neural networks. So typically, how many layers and nodes of neural networks are sufficient for automotive radar applications?
Well, of course, this depends on the radar application, what you want to do. I can just tell you what we did in this approach where we applied neural networks for directional horizon estimation, and there we just had 2 or 3 hidden layers where each layer had 128 neurons. So we really focused on low complexity feed-forward networks, because one interest also is that they have to be, regarding the computational, let's say, resources, they of course must be able to compete with this maximum likelihood approach which we have today. And then also for interference classification, of course, you keep it maybe in the same manner. So typically it's very, very small neural networks which are of interest here. Neural networks for replacing simple signal processing steps for embedded applications. So not the big ones, like you look once or something which you typically use for image recognition and classification.
Okay, so I think that's it from question side. I think we should conclude this talk now. Thank you very much, Professor Markus. It's indeed a pleasure for us to hear your talk, and we're very hopeful to see you in Pakistan after this pandemic.
Yeah, thank you. Would be my pleasure. To visit Pakistan in person. Thanks.
Thank you very much. Thank you, audience. Now I'm concluding this webinar and hope to see you in the next webinar talk on 5th of October. Thank you. Bye-bye.